Hi everyone, welcome to the short paper introduction. Today I'm going to talk about flow matching for generative modeling. Before we start, I want to mention that the goal of this video is to help you quickly grasp the overall concept. If you find this paper interesting, I recommend reading the full paper. By the way, I'm Jaegonim and I'm super interested in generative models, especially for audio generation and processing. I'm a PhD student in the Music and Audio Computing Lab at KAIST. Okay. Why is this paper interesting? This paper introduces a new paradigm for generative modeling based on continuous normalizing flows. I will explain what that is in a few minutes. Understanding this paper will provide you with the fundamental background needed for Stable Diffusion 3 and Meta Movie Gen. Alright, let's get started. Let's start by talking about the diffusion model. The diffusion model is a score-based generative model because its training objective implicitly computes score at each noise scale. If you are not familiar with what that means, I strongly recommend reading the reference at the bottom of this slide. The score function defines a vector field over the entire data space. If you are not familiar with a vector field, you can think of it as representing the velocity of a moving flow. This vector field generates a probability path. How is all of this determined? By diffusion process. Okay, so what are the limitations? As mentioned earlier, probability paths are determined by the diffusion process. We don't have the freedom to choose an arbitrary probability path. This results in a confined space for sampling probability paths. Such constraint can lead to problems like long training time or the need for specialized methods to achieve efficient sampling. So, how about considering general probability path? Continuous normalizing flows are generative models capable of modeling arbitrary probability distributions. However, it requires expensive numerical ODE simulations, so there were not many algorithms for scalable training. Even if you don't know the previous works, it doesn't really matter for understanding this paper, so don't worry. To address the limitation, this paper proposes flow matching, an efficient simulation-free approach to training CNF models. They introduced the flow matching objective based on regressing vector fields. Let's define the terminology first. A data point X is a d-dimensional vector. The probability path is time-dependent, meaning that for a given time between 0 and 1 and the d-dimensional vector, we can obtain the likelihood. We want to set P0 to a standard normal distribution and P1 to be approximately equal to the data distribution Q. As you might expect, we want to sample X0 from standard normal distribution P0 and then transform it to follow P1. Flow is a time-dependent diffeomorphic map. You can just think of it as the position of the data at each time step. Finally, there is a vector field which is also time-dependent. As mentioned before, it is kind of velocity, so the derivative of flow would be the vector field. Please remember that this vector field is what we want to know. Why? If we know this vector field, we can first sample the data from the normal distribution P0 and then, by using an ODE solver, compute the data following the P1 distribution. Before we move on, I want to explain the relationship between the probability path and the vector field. So, how can we make sure a vector field really creates a probability path? The continuity equation provides the necessary and sufficient condition for this. A detailed explanation of the continuity equation is beyond our scope, so I will just briefly explain this. The equation in the red box is divergence. A simple way to understand divergence is by thinking of it as how much each point is moving out from the origin or moving in towards it. I think this figure helps with understanding intuitively. In the first figure, the divergence is positive because everything is moving outwards. In the second figure, the divergence is negative because everything is moving inwards. The last figure shows zero divergence because there is no spreading out or in. If a vector field truly generates a probability path, then the divergence of PTX, VTX indicates how much probability density is moving in or out. Therefore, the negative divergence will be derivative of ptx. Now we know how to validate if a vector field generates a probability path. Please remember this as we will use it later. Okay, so how can we train our neural network to learn vector fields? For this paper proposes a simple regression task, flow matching objective. So theta is the trainable parameters, and t is time, sampled uniformly. It is similar to diffusion, right? Vtx is the output of neural network. And finally, utx is a vector field, which we want to know. Okay, everything is so simple. Is this end? Unfortunately, we don't know the ground truth vector field. Then, what are we gonna do? For a simpler way, let's define the conditional probability path. Conditional probability path is a simpler probability path which depends on only a particular data sample. Just one data sample. When t is 0, it is the same as the marginal probability. And when t is 1, it is a Gaussian noise having x1 as a mean. We can also define conditional vector field that generates conditional probability path. They define marginal probability path and marginal vector field. If you see the formula of marginal probability path, it is straightforward, just aggregating the conditional probability path. However, you may think marginalization of vector field seems a little bit not that straightforward, but you'll see why this aggregating method is reasonable. By the way, why are we discussing conditional probability path and vector fields? What we actually want to know is the marginal probability path and vector field. Are they related? The answer is yes. This is the theorem 1 in this paper. If the conditional vector field generates the conditional probability path, the marginal vector field generates the marginal probability path. Okay, let's prove this. Remember, if we want to demonstrate that the vector field generates the probability path, we need to show that this continuity equation holds. Let's check one by one. First, substitute ptx with the marginalization formula we saw before. We assume that a conditional vector field generates a conditional probability path, so we can use the continuity equation here. Now we can see how the marginalization of vector field makes sense. Let's substitute. Finally, we show that continuity equation holds. That means if the conditional vector field generates the conditional probability path, the marginal vector field generates the marginal probability path. This connection allows us to break down the unknown and intractable marginal vector field into simpler conditional vector fields, which are much simpler to define as these only depend on a single data sample. Wait, even though conditional vector fields are simpler, we still need to calculate the marginal vector field. However, the integrals are intractable. This means we can't train our model using the flow matching objective. This paper presents a very interesting observation that conditional flow matching objective, which uses a conditional vector field instead of a marginal vector field, can give the same gradients to model. Therefore, we can use the conditional flow matching objective to optimize our models. This is really nice because without access to the marginal probability path or vector field, we can still train the model to generate the marginal probability path. Now let's prove this. This is theorem 2. Let's demonstrate that the gradients of conditional flow matching, CFM, and flow matching, FM, are equivalent. The formula above represents the FM objective, while the formula below corresponds to the CFM objective. Let's expand the square of each formula. Alright, these are simply expansions. Now we want to show that the gradients for each objective are equivalent. First, the less parts in each expansions are independent of theta. Therefore, we can disregard these terms. Now I will demonstrate the equivalence of each term in the blue box and the green box. Let's start with the blue box. As you can see, the expectation is represented by the integral. By using the marginalization property, we can transform ptx like this. Next, we can express this term as an expectation. With that, we have confirmed the equivalence in the blue box. Now, let's proceed to the green box. First, we can transform utx using its marginalization formula. And then, we can remove ptx. Due to the linearity of the integral, we can exchange it with the inner product. Finally, we have confirmed the equivalence of the formula in the green box, which means that the gradients of conditional flow matching and flow matching are indeed equivalent. Therefore, it is valid to train our model using the conditional flow matching objective. Now, let's explore how we can select conditional probability path. We can select any probability path. In this paper, they choose Gaussian conditional probability path. They set the mean to 0 and the standard deviation to 1 at t is 0, which means px follows a standard Gaussian noise distribution when t is 0. When t is 1, the mean is set to x1, and the standard deviation is set to sufficiently small value. Thus, when t is 1, P1x x1 is a concentrated Gaussian distribution centered at x1. They choose to use the simplest vector field. The flow psi-tx is an affine transformation that pushes the noise distribution toward Ptx(x1), which has a mean mu-tx1 and standard deviation sigma-tx1. Here, x is distributed as a standard Gaussian. As a reminder, x1 refers to a specific data sample. Then, we can get a loss form like this. The vector field is obtained by taking the derivative of the flow, and we calculate the CFM loss using this as the target. Now, let's derive the exact form of this vector field. The formula in the blue box shows the vector fields. I will explain how this form can be derived. For notational simplicity, let's define WTX like this. Then we can rewrite UT psi TX x1 as WT psi TX. We let psi TX is Y, so we can make formula simple like this. Deriving the derivative of psi tx is straightforward. Deriving the inverse of psi t is also straightforward. By substitution, we can obtain the formula for the vector field, which is the target for the CFM loss. Let's briefly summarize the learning method once again before moving on to the next part. There is the flow defined simply by the differentiable function mu t and sigma t. This flow provides a vector field. As we saw earlier, we can derive the exact form of the vector field. We use this vector field as the target of the CFM loss. After training, we can sample the data by using trained vector field and ODE solver. Now, let's look at the specific examples of mu t and sigma t. We are free to choose mu tx1 and sigma tx1 as long as they are differentiable functions that satisfy the required boundary conditions. Let's see the special case. In the table, you can see the choices of mean mu tx1 and standard deviation sigma tx1 that correspond to probability paths for diffusion processes. I won't go into the details here as the diffusion path is not our main focus. However, you can simply understand that we already know the diffusion path for both the variance exploding and variance preserving cases. So we select mu tx1 and sigma t x1 accordingly. Yep, but as I said before, diffusion path is not our main interest. Now we have the flexibility to choose mu tx and sigma tx, so why not simply set them to change linearly over time? This is the optimal transport path that we are more interested in. To obtain the vector field, let's just use the formula we derived earlier. Then we have loss function like this. This intuitive figures illustrates that the optimal transport OT path is straight, while the diffusion path is curved. OT path conditional vector field has constant direction in time and is simpler to fit. If you look at the figure on the left, you will see that the model trained with flow matching using an optimal transport path generates the 2D checkerboard pattern faster than other methods. If you see the figure on the right, you can check that flow matching with OT path model can generate checkerboard pattern with just NFV 4, although the other models is not able to do that. Flow matching with OT path demonstrates superior performance over other methods, including DDPM and score matching on the CFAR and ImageNet datasets. Figure 6 also shows that flow matching with OT path models starts generating images sooner than the diffusion path models. Okay, this is the end of this video. Thank you for watching and always welcome for discussion. See you next time.